Okay, so this section 6.1 is a little bit short compared to we're doing some terminology here, and there's kind of one procedure we'll look at. And it's really kind of just pushing forward what we did in past chapters, quite a while ago now, when we were solving differential equations here, and we had something like y double prime plus 3y prime plus 2y equals x. All right, so this right here is a perfectly good linear differential equation, right? And the whole idea of it being linear was that you need to have it in the form some coefficient of x with the nth derivative plus some other coefficient, maybe involving x, and then the next smaller derivative all the way down to some coefficient of x with the first derivative and some coefficient of x with the regular function equals some other function over here only involving x. So this was the standard form of a linear differential equation of nth order. And the only ones we really solved were second order or third order, and specifically where all of these things were constants, these coefficients here. But you can still look at this as a general theory and trying to see what's going on in here. And there was one thing we kind of saw before, was that when it was a second order equation, you were going to get two roots or a double root of the polynomial you solved. So for example, looking at this one here, when we did our auxiliary equation, s squared plus 3s plus 2, and we get two answers here, should be -2 and -1. And so that meant our homogeneous solution was c1 e to the -2t plus c2 e to the -t. And remember, the whole thing was we had to have these two answers here if it was a second order equation. And if it was a third order equation, you'd have to have some third term over here. And I am focusing on the homogeneous part here. And it turns out if you have a fifth order, you're going to have 5 different ones. And remember when we said if you had a repeated root, we had to add in something extra, the extra t in front of it. And all of that was because of the following idea here, is that we want y1, y2 to yn to be linearly independent solutions to the nth order linear differential equation. And so if we had a second order, we're going to want 2 of them, third order 3, and so on here. But I do really want to call attention to this. We never had anything about independent back on exam 1 material. When we were doing differential equations before, there was no independent or dependent issues. And so now we get to kind of bring that in and kind of review what we covered before. And what does it mean? So how do we know e to the -2t and e to the -1t are linearly independent? Because if they were dependent, then we would not actually be done solving the problem. And it turns out there's a really straightforward way that we can check this here. And so let me start over here. And this is going to be called the Wronskian. And so here's how a problem might be. We would say check whether e to the -2t and e to the -t are linearly independent. And here's how it works. So the way the Wronskian does is you take a new matrix, a new determinant even, and you put not numbers here, but the two functions you have across the first row. And then in the second row, you take the derivative of each one of those. So this would be negative 2 e to the negative 2t and negative 1 e to the negative t. And then you're going to take the determinant of this thing here. And if I do e to the negative 2t times negative e to the negative t, I'd get negative e to the negative 3t. And then minus, and the other one's going to be a negative 2 e to the negative 3t. And this ends up becoming a positive 1 e to the negative 3t. And the thing is, when you take this determinant, as long as you don't get 0, then they're going to be independent here. So since the Wronskian is not 0, then the two functions are linearly independent. Now you can do the same thing here if you had a third order and you had 3 solutions. If you were going to do a Wronskian of 3, you write out all 3 functions on top, and then the next row you take the derivatives of each. And then because you need it to be a square matrix for determinant, you go to the second derivatives for the third row. And if you work all this out here and you ask whether it's 0 or not, then you can determine whether these things are independent or dependent. Now, I'm not going to make you do a 3-function one, but I could very easily ask you to do a 2-function one here. And this is the main thing for this section, is how do you check whether functions are independent or not. And it's not going to tie in too much into what we're doing the rest of the semester. It really fit in better with the exam 1 material. The only problem is on exam 1 we didn't have determinants yet and we didn't have independent yet. So it's just kind of thrown in here at the end of the semester. So what I want you to be able to do is I want you to be able to check using the Wronskian whether 2 functions are linearly independent or linearly dependent.